Good afternoon, everybody. Thank you for coming back. Thank you for visiting the expo booths. I hope that you found something interesting there to explore. It's my great pleasure to introduce our third speaker. This is Matt Mcfarland. Matt works on the Microsoft Planetary computer and is going to talk a little bit about that project. He's a geospatial software engineer specializing in open source and environmental sustainability work at Microsoft. And I will hand it over to Matthew.
All right, great. Thank you, Arthur. And I think my screen has come up. So hello, everyone. Good afternoon. I'm Matt Mcfarland, a software engineer at Microsoft, working out of an unseasonably warm Philadelphia, Pennsylvania today. I'm joined also, like every day, by my cat, who may make an on-camera appearance if we're lucky. So for the last year, I've been working with a small team at Microsoft on a project called the Planetary computer, which I'll admit is not necessarily the most self-descriptive name. So today I'm going to talk about what exactly the Planetary computer is, why we've identified a need for it in the community, and where we see it going. If you're attending a location intelligence conference, this statement will come as no surprise to you, but it's the central premise for developing the Planetary computer. We're experiencing an explosion of data about the Earth. Remote sensing programs from big government agencies like Landsat, Sentinel are continuing to operate and indeed launch new satellites. Landsat 9 is streaming back data as we speak. New space companies launching small-scale platforms. New, or at least newly commercialized instrument types like SAR and hyperspectral are coming to market. And not only is new data growing, but the archive of existing data is also becoming increasingly important as we seek to understand how the planet's systems have changed and to predict how they will continue to change. But just because that data exists and is made available doesn't necessarily mean it's accessible. This is a huge problem because there's so much technical expertise, time, infrastructure required to get at this data, to find what you're looking for, set up compute resources to actually be able to use it. But it's also an opportunity for new solutions, one that Microsoft, with its cloud platform, Azure, has a unique opportunity to participate in. The project has been launched within the environmental sustainability group at Microsoft. And while there are many use cases for geospatial data, working with environmental data and answering environmental questions is fundamentally a geospatial problem. And it's complex, increasingly so. The main sources of friction that we see are disparate data sources. Geospatial data comes from a wide variety of data sources, providers, different data formats, storage locations, coordinate systems, access patterns. The number of different ways to get at data about our planet can be confounding and requires that technical knowledge and effort that I mentioned. To get the data needed for a single application or research task, it's common to want to combine optical imagery, digital elevation models, say land cover classification, and all of that data may be available as a mix of, say, GeoTIFF, JPEG 2000, NetCDF. It might be available on an FTP server. This means that step one for using this data is a lot of data downloading and data preparation. There's also the volume of data. Earth systems data represents some of the biggest data sets we can think of. And as I mentioned, they're only getting bigger. The NASA Earth science data alone is expected to increase from about 32 petabytes to almost 250 petabytes in the next few years when they start launching some new platforms. There's also the idea of access. So the ability to access geospatial data easily is a roadblock for all the subsequent steps to using the data effectively, from performing conventional GIS analysis to developing more advanced ML and AI models to provide insights and analytics. Then when there is physical access to the bytes, the next question is, are the tools and libraries I want to work with able to use them? And the last problem we see is this sort of compute at scale problem. The ecosystem of tools to access and process this type of data has been growing, but it faces challenges in the age of the cloud. So many users of geospatial data download data to their local machines, and tools expect to operate on data on the file system. Distributed processing is complex, but it's also necessary when the volume or the resolution causes data to exceed the amount of memory you have on a single machine. So the Planetary computer is an effort that's being developed to address these main issues. Stepping back a bit, at Microsoft, we've been working on sustainability for a while. It's been more than a decade since our first carbon emission reduction goal in 2009. Since then, we've made steady progress. One of our most significant milestones was in 2012 when we committed to being carbon neutral. We achieved that goal in 2013 and every year since, using what at the time was a novel approach of establishing an internal carbon fee. We charge our business groups an actual price on carbon based on their specific emissions, and then we invest these funds towards our sustainability goals. When we sat down a few years ago to draft our sustainability plan going forward, we knew that we needed to match the scale of the environmental challenges facing the planet. Leaning on our roots as a software engineering company, we had sustainability sprints over the course of the year, asking questions like, what does the best available science say that we should do? What do our customers and stakeholders expect of us? What can we accomplish? And I kind of think, importantly, how can we use our resources to scale efforts for other organizations? Every 3 months of that year, we focused on a different area of sustainability, and each sprint culminated in a new industry-leading sustainability commitment. The first came out in January 2020 when we announced our carbon negative commitment. By the end of the year, we had committed to being, by 2030, a carbon negative, water positive, zero waste company. But more directly related to this talk, we also committed to building and operating the infrastructure for a planetary computer to better monitor, model, and ultimately manage the world's ecosystems. The idea being that the technical infrastructure we require to make progress towards these commitments could also accelerate our customers' sustainability journeys. Our ecosystem initiative is multifaceted, but one of the aims is to put data and digital technology to work, including through a program to aggregate environmental data from around the world and put it to work in this planetary computer. So I'm going to go through and talk about sort of the major components or sort of goals of the planetary computer here. But at its core, it's a geospatial data platform. And the core value proposition is bringing together crucial data sets being used for environmental sustainability within the Azure cloud. This generally means just copying entire archives of global data sets, creating data pipelines to acquire new data streams as they're being constantly generated, and again, bringing them into Azure. This isn't an exhaustive list, but it conveys the major categories of data that we're hosting so far. We've focused heavily on remote sensing products initially, along with weather and climate data. But like I said, digital elevation models, land cover, operational weather forecasts, things like that are all part of this system. We're also working through a backlog of data sets that we know are valuable and to get them available in the planetary computer. We do really value the input from customers on how to prioritize new data. So please do reach out and tell us about your needs. We'd love to be able to bring more data onto the planetary computer. So what does it mean for us to host one of these data sets on Azure? Like, what does that mean exactly? So for each of these that I have here and that are in our catalog, we bring almost everything into the West Europe Azure region. The specific region is not really important, but the fact that they're in a single region is important, and I'll pick up on that a little bit more when I talk about compute. We then convert to a consistent cloud-optimized file format. We use COGS, cloud-optimized geotiffs for images, ZAR for climate and time series data, Parquet for tabular data. And we're also experimenting, excuse me, with a few newer formats, the so-called cloud-optimized NetCDF for large archives where reprocessing may not be ideal, and something called COPC, cloud-optimized format for point clouds. We then store these on our low-latency HTTP accessible object store, blob storage, and we also process them to be analysis ready. So, for example, atmospherically corrected in the case of some imagery products. Since these are all in open standard cloud optimized data formats, they're available over HTTP, they're all readable by familiar tooling like GDAL and Rasterio, Xarray, Esri tools. We don't provide a proprietary solution here at all. As a result, this data is interoperable with existing tools, and I think importantly, it will be interoperable with new tools and frameworks as they come out because they target these same kind of file formats. You can go online right now after my talk and browse the available data sets we have in our data catalog. Here's a little screenshot. This is where we show important metadata about the data. We have examples on how to access it and how to use it. I also personally like the site because it gives me an opportunity to just make pretty thumbnails of interesting spots on the planet. We also have a search and visualization tool called the Explorer. This provides a GUI for building data queries against our catalog. Shows the results as mosaic images on a map. It can auto-generate Python code to work with the same data, like search results in an analytic environment. And it's also just a great way to casually explore the data, get familiar with it, get familiar with the properties, see what kind of resolution it's in, what kind of features are visible in it, what the temporal range is for a given area, etc. So it's another part of the Planetary computer that's worth checking out. So basically, this covers the step for assembling the data to get at that one problem about all these disparate data sources. The next core goal is to provide some standard access to these data. This is the needle in the haystack problem, where despite the vastness of an archive or the many archives, you may only be interested in a particular spatiotemporal slice of it. Traditionally, access to individual data products within a data set, for example, grabbing just the green, blue, and near infrared bands from a set of Landsat 8 scenes, often relies on understanding sort of idiosyncratic directory structure and file naming conventions. Instead, with our core metadata API, you can query all data sets against space and time properties, as well as other indexed attributes of the metadata, like cloud cover, for example, or sensor name, depending on the data set. And rather than invent a proprietary metadata and search standard, we've embraced and supported a community-driven effort around STAC. So STAC stands for Spatiotemporal Asset Catalog. And this is really the core of the Planetary computer in a lot of ways. It's the enabling technology that we've built our services on. If you're not familiar with STAC, I really recommend that you visit stackspec.org, check it out. There's a lot of tools. It's a great community for people looking to implement or just consume. But it defines a standard way of encoding metadata as JSON for any type of spatiotemporal data, as well as a common API interface for querying that metadata. The metadata is formalized at the dataset level, which are called collections, at the item level, which would be analogous to like a scene, and for the multiple file assets that may be attached to an item or scene, again, like bands in an electro-optical dataset. It relies on and is sort of aligned with core OGC feature API standards. So it's not a sort of brand new thing out on its own. And it uses the same kind of query language and schema elements. And it's being implemented by a number of data processors and producers. As a result, we provide a metadata querying experience that is already familiar to many working with geospatial data, and it's interoperable with a large body of community developed tooling. This is important because though we may not yet be able to host every data set you want to work with, we really envision a world where the tooling and the workflow can be consistent between data providers. So now we've curated, collated, and indexed a lot of the important environment data and consolidated it in the Azure cloud. We're operating an API service so we can search and filter on the metadata, find Landsat scenes over Wyoming in 2017, where cloud cover is less than 20% or something like that. And this is all really fast because we haven't yet had to open and read any files. But of course, that's the next step in any workflow, is that you want to get at the bytes. So the last core offering of the Planetary computer is to provide some foundational services for doing analytic work, because that's the actual value of having accessible data. It's to make it available for analysis and applications and insights. So that brings us to the last component of the Planetary computer, which we call the hub. In keeping with the theme of investing in and embracing existing community tools, we offer a hosted Jupyter Lab cluster. Again, this should already be familiar to a significant portion of our audience. Users have compute resources provisioned via Jupyter Hub. They have popular geospatial and ML tools pre-installed and pre-configured, sort of pre-set up to work with the Planetary computer. The environment is also pre-configured with a Dask gateway for performing synchronous distributed processing and a Kubernetes-based asynchronous batch processing system. Those are both sort of complex infrastructures that support these environments, but they're more or less opaque to the user in the sense that they don't have to set anything up or worry about the deployment. We just expose standard APIs and tools and let people work with them directly. Importantly, this compute environment is hosted in the same region as our data. So this enables fast and efficient reads, again, over HTTP typically, because these are cloud optimized file formats. But the ideal sort of workflow would be that people are never downloading this data to even this compute environment, the hub or their local computer, but rather they're sort of streaming in byte range requests from our HTTP blob service for these files, using these metadata services, these API services, to sort of find the files that they need. However, for users that need to scale beyond that offering, like we do have some limits on the number of cores and the disk space that are allocated within these Jupyter clusters. For folks who need to scale beyond that offering, the entire hub environment itself is open source and is based on Pangeo toolchain, and it can be deployed in their own Azure subscription. Users can also connect to our remote Jupyter Hub hosted kernels through other tools like VS Code and GitHub Codespaces if a sort of hosted notebook environment is not ideal. So to reiterate that theme, Planetary Computer geospatial data platform, with the goal is to make it easier for users to actually start doing their work and spending less time doing all the sort of technical infrastructure work to get data in the right format and get compute environment. Since it's in a cloud optimized format using the standard metadata, having distributed processing is available. All the tools are in place to do large scale out of core processing. You can start evaluating data, doing experiments, and then scaling up to regional and even planetary scale processing jobs. We've also taken a completely open approach to the platform in line with the Pangeo community. The data is openly licensed. The tools, the standards, and even our own application code is open source, available on GitHub. The platform itself, the API, all the data are all open access, which means you can use our APIs and the hosted data even without any account, completely anonymously. Though with a free account, you do get access to the hub and to higher tiers of throughput through the API. And this is mostly a mechanism for us to manage our egress costs. We've also been working with a number of partners that I wanted to highlight. They're using our data and APIs. We launched with a collaboration from Impact Observatory and Esri, who were using Sentinel-2 imagery from the Planetary Computer to develop a deep learning model to generate 10-meter annual land cover maps globally. And you can check these out on our website. So that is the short run through of the Planetary Computer. I think I might stop now for questions, and then depending on how many there are, go through and sort of poke around the website and show off some of what we have.
Well, that's really good, Matt. Thanks so much for that. I have to admit there were a couple of things there that I wasn't familiar with, so that's interesting. Now, I don't have a lot of questions yet, but I have a couple of my own questions.
Sure.
The first one was, so one of the things that sort of sets the alarms off for me a little bit is actually copying the data, because once you copy it, then it's a copy. And if the original author updates it, then you got to copy it again. Have you thought a little bit about how you might federate that with other people's data? So like a federation link in some fashion?
Yeah, so we're actually very interested in a federated approach. We don't, although that is not sort of a current feature of the system, we do, however, have basically pipelines for refreshing data. So I don't know all the technical details, but there was recently some sort of recalibration that was done on the Sentinel-2 platform. And that it required some offsets to be applied to some of the data that was coming back. So in our system, and in fact, anybody's system who is sort of reproducing some of this ESA data needs to have a process to both back process part of the archive data and make sure new data coming in it has the fix. So yeah, so our approach right now is to have jobs that are constantly running and both getting new data, but detecting changes in the upstream and reprocessing, reapplying, and sort of keeping our catalog fresh. We're right now syncing about within a day of new data, making it down from its sort of upstream sources into our catalog and available.
If I were Microsoft, I think I'd be trying to make a move that the Planetary computer actually becomes the authoritative source. So if you're let's say you're a satellite operator and now you've got to provide your ground station processing and all that stuff, surely that would be easier to just plug it straight into Azure and solve the problem that way.
Yeah, well, you and I both agree about that. Yeah, and in fact, there are other. So there's an Azure Orbital service that has a ground station sort of operational.
Yeah, that's kind of where the conversation came from.
Yeah, and of course, the effectively the deluge of data that is now streaming down and certainly is only going to increase exponentially. Having a cloud, having Azure is basically it's going to be a necessary component of any of those strategies, just for the storage and managing egress costs and things like that. So yeah, we would love the Planetary computer to sort of become a more integral part of that process. Some of the open access data that we have coming from, say, like USGS, NASA, NRCan from Canada, I think they have some mandates about how they like the provenance of their data and where it's stored. So we may not, we may need to be making copies of it, but yeah, we have direct relationships with a lot of those groups where they're actively pushing to our Azure storage rather than us having to pull from it.
The question I was actually expecting to see in the Q&A was, how's this financed?
Well, so it's like I mentioned, we're not charging access for it, as I mentioned. We don't currently have a roadmap for that. We're being like I mentioned, we're being run out of the environmental sustainability group, so it's basically being financed ultimately from the budget that's allocated to that, which is partly from this carbon tax, in fact, this internal carbon fee that we charge. So right now we're definitely in the proving out value stage, getting customer feedback stage, and trying to see what it looks like for the long term.
That makes sense. I mean, it's kind of a curly question because if I suddenly develop my environment and sustainability strategy based on this tool, and then all of a sudden the tool starts getting you start getting charged for it, then people will look at that and go, hey, wait, that's not quite pure. I should know up front, right?
Yeah, absolutely. We're super concerned about that and building up the sort of trust and goodwill. I will say one thing that it's a technical response to that, which is maybe a good thing. But most of the data that we have that we're offering and that accounts for the vast majority of usage. Like let's say we have 50 some plus data sets. The most of the bytes that are getting moved around in people's application process are like concentrated in a couple collections that are really popular, which are the big satellite, like the remote sensing products. All of those are, you can't charge money for access to those. Like those are free public use data, which is why we're taking this no even account required, because they're for the public good. They're paid for by tax dollars. Like they're going to remain free and accessible.
Yeah. I can imagine organizations like the Red Cross
Yeah,
being interested as well.
I think we are focused on environmental sustainability, but we are taking, and that's driving our curation of the initial data sets that we're onboarding. But analytics is analytics, geospatial analytics is geospatial analytics. Like we're interested primarily in supporting use cases around ecosystems and climate risk and sustainability in general. But there's a wide range of use cases that I think that this platform would benefit.
Perfect. Well, that's great, Matt. There's no questions over here, so I think we can probably close this. And I would invite anybody who's interested. The team is suggesting that we direct folks to the lounge in case you have further conversations that you want to have. We'll go.
Yeah, I'll head over to the lounge, and if I can share my screen there, I'll sort of have the site up and can poke at it if folks are interested.
That would be interesting. Yeah, that's great. Well, thanks once again, Matt. We really appreciate you coming and telling us about it, and I'm glad to learn about it. I didn't know much about it before.
Great. Yeah. Well, thanks for the invitation. Take care.